in order to understand why there are average masses and not just a single standard mass for a single element, we need to recognize that although an element is identified on the basis of the number of protons its nucleus contains, this does not restrict the number of neutrons nor the number of electrons that an atom may have. So long as an atom contains one proton, for example, in its nucleus, regardless of what else is there or not present, we still refer to that atom as hydrogen. And although we can vary other characteristics like mass and charge for hydrogen, so long as it retains a single proton in its nucleus, it is still identified as hydrogen. If we change the number of neutrons that are with the single proton in the nucleus of a hydrogen atom, we start to change the mass of the resulting atom. Because protons contribute a mass of 1, and neutrons contribute a mass of 1 to the total mass of an atom, then we can say that the total mass, or mass number, for an atom, abbreviated capital A, is the sum of all of the protons plus all of the neutrons that make up that atom. For example, in this leftmost version of hydrogen, there is a single proton and not a single neutron in the nucleus. We'd say that the mass number, capital A, is equal to 1. In the middle picture, there is a single proton and a single neutron in this nucleus. We'd say that the mass number is equal to 2. In the third picture, there's a single proton and 2 neutrons in the nucleus. We'd say that the mass number here is equal to 3. And although this mass has changed, the identity of the element is still hydrogen in every case, because in all cases there's just one proton in each nucleus. We call these variations of hydrogen that differ in terms of mass isotopes. Isotopes are the same element, just with different masses for different atoms. They vary in mass number because they vary the number of neutrons that their nucleus contains. Hydrogen, it turns out, gets special names for different variations of its isotopes. Sometimes we call hydrogen with mass 1 protium, hydrogen with mass 2 deuterium, and hydrogen with mass 3 tritium. But it's also perfectly acceptable to call each one of these hydrogen and just say its name of element followed by its mass number. For example, hydrogen 1, hydrogen 2, and hydrogen 3. Of these 3 variations of hydrogen, by far the most common is hydrogen with a proton and nothing else in its nucleus. Less than 1% of all hydrogen atoms that naturally occur on Earth consist of 1 proton and 1 neutron in the atomic nucleus. And finally, 1/trillionth of 1% of all of the hydrogen atoms that naturally occur on Earth have 1 proton and 2 neutrons in their nucleus. So by far, protium, or hydrogen with mass 1, is the most abundant version of hydrogen that we find. Therefore, when we take weighted averages that are based on how much of an isotope naturally exists on Earth and the mass of that corresponding isotope, we report on the periodic table a mass for hydrogen that is very close to the mass of this protium version of the element. If we looked up the mass of hydrogen according to the periodic table, its average mass is 1.008. This is because, far and away, most of Earth's hydrogen atoms consist of just one proton in the nucleus, with no neutrons at all. Therefore, as we look at the periodic table for mass numbers, those mass numbers can be deceiving. They're an average mass of all variations or isotopes of elements. To help us simplify the symbols for isotopes, we use shorthand notations. Because we might deal with things on a small scale, sometimes chemists are interested in distinguishing specific isotopes from each other. To do so, we write an element symbol, X, to take the place here. As a superscript, on the left-hand side, we write the mass number for that isotope. That's the combination or total number of all protons plus neutrons that this particular version of an element contains. Optionally, as a subscript on the left-hand side, we can include the atomic number. This is optional because the atomic number is always implied by the identity of the element itself. We can always just go look up element hydrogen on the periodic table, for instance, and see that it's atomic number 1. So we don't always have to include this quantity, a subscript, to identify the atomic number or number of protons that an element contains. An alternative to writing an isotope symbol like this is to write everything all in one line with an element symbol followed by a dash and the mass number, the number of protons and neutrons. Again, the element symbol implies the atomic number because we can just go to the periodic table and look up what our element symbol is. To give you a few examples, let's look at some isotopes of different elements. We'll consider the isotope symbol, the number of protons that that isotope contains, the number of neutrons, and the number of electrons. And we'll study these 4 isotopes. So, we've got element symbol U, to the left a superscript 238, to the left a subscript 92. According to the convention of this leftmost depiction of our isotope, the subscript on the left indicates the atomic number. This is the number of protons that this element contains. Element U, uranium, atomic number 92, will always have 92 protons in its nucleus. We can determine the number of neutrons by rearranging the definition of this mass number. A mass number is equal to the number of protons plus the number of neutrons. If we know a mass number, and if we know a number of protons, because we know an atomic number, then we can rearrange this and say that the number of neutrons is just our mass number minus our number of protons. In other words, our mass number, the superscript on the left, minus our number of protons, gives us our count of neutrons. 238 minus 92 is 146. Because elements on the periodic table are assumed electrically neutral, and because we haven't been given any evidence to the contrary here for uranium, we're going to say that the number of electrons must be equivalent to the number of protons in order to maintain electroneutrality. 92 electrons for 92 protons. For the next isotope, Cl37, which we'll say is chlorine 37, now only explicitly gives us a mass number in the convention of this second depiction of an isotope. The best we can do to figure out the number of protons is to look at the periodic table. On the periodic table, we see that chlorine is atomic number 17. That means that any variation of chlorine must always have 17 protons. And to be electrically neutral, it also needs 17 electrons. The number of neutrons comes from the mass number, 37, minus the number of protons, 17. There must be 20 neutrons in this version of chlorine. For the next isotope, sodium-23, we're not given explicit information about the number of protons because we're not given a subscript on the left-hand side. So we're going to have to go to the periodic table once more and find that sodium's atomic number is 11. Therefore, it has 11 protons in its nucleus. If it's electrically neutral, it also has 11 electrons to balance out the positively charged proton. The number of neutrons comes from the mass number minus the number of protons. 23 minus 11 is 12. Lastly, for carbon-13, we look and see that on the periodic table, carbon is atomic number 6. It has 6 protons. Electrically neutral carbon, therefore, must have 6 electrons. And lastly, the mass number, 13, minus the number of protons, 6, gives us the result of 7 neutrons in the nucleus of carbon-13. In a PDF and video that follow, I've walked you through and have given you the opportunity to do more practice with counting the numbers of protons, neutrons, and electrons in isotopes and in charged ion versions of isotopes. We're going to talk about electron variation next, but if you want more practice walking through these steps, see the corresponding video and worksheet that I've posted on your Moodle page. So by this point, we know that variations of elements called isotopes exist and that the average masses reported on the periodic table come from the masses of those respective variations. But what we need to do now to wrap things up is to figure out how we report those average masses in the first place. Where do they come from? To introduce this, I have an example for us to work through. For carbon in particular, there are 2 naturally occurring stable, meaning non-radioactive, isotopes, carbon-12, which has a mass of exactly 12 AMU, and a natural abundance on Earth of 98.930%. The other isotope of carbon that naturally occurs on Earth is carbon-13, which has a precise mass of 13.00335 atomic mass units. We're going to calculate the expected average isotopic mass of carbon for inclusion on the periodic table. So how do we do that? Well, we need to know how to calculate an average mass in the first place. Calculating an average when different components of that average have different weights isn't as straightforward as adding things up and dividing by the number of things. Rather, we have to compute what's called a calculated weighted average. A weighted average, if you remember from your math class, and you're mathematically minded, is the sum, that's what this sigma symbol means, of all of the respective weights, those are effectively the percentages from this question up above, multiplied by their corresponding values. In this case, it's the masses of each respective isotope. Another way to put this that's a little bit more direct is that we, in turn, multiply the percent abundance of each isotope by its corresponding mass. Isotope number 1's abundance multiplied by isotope number 1's mass. Add to that the product of the abundance of isotope number 2 multiplied by its mass, the abundance of isotope number 3 multiplied by its mass, and so on and so forth for as many isotope variations as we've got for a particular element. In this case, there are only 2, so we really only need these first 2 terms of this sum. We're not going to divide by the number of elements involved in this average because taking a weighted average factors that into consideration already by multiplying by a percent or weighting each one of these isotopic masses in the first place. So, all we need to do to come up with a weighted average is to be given percents for each one of our isotopes and masses. We've already got a mass for isotope number 1. Let's call that carbon 12's isotope. And we've already got a mass for isotope number 2. Let's call that carbon 13's isotope. We have a percentage for isotope number 1. That was for carbon 12. That's 98.930%, but I didn't give you a percentage for carbon 13's natural abundance. So we're going to have to figure that out for ourselves. So how do we get this quantity? Well, let's think about what we know. We know that there are only 2 naturally occurring isotopes of carbon on Earth, and that together, all of these carbon isotopes account for all of the carbon that's on Earth. So that must mean that 100% of carbon is due to carbon 12 and carbon 13. We know what percent carbon 12 constitutes, so let's subtract that from 100 to figure out what percentage carbon 13 represents. Exactly 100% of carbon is due to carbon 12 and carbon 13, and the percent abundance of carbon 12 is 98.930%. Subtract that from 100, and we get the percent abundance of carbon 13 as 1.070%. So in this way, by using some deduction, we can determine the percent abundance of our second isotope. And now we have everything necessary to plug and chug into this weighted average equation boxed in up above. The weighted average for carbon's isotopes is given as the percent abundance of isotope number 1, which we called carbon 12. That's 98.930%. I can't multiply a percent directly, so I'm going to convert it into decimal form. So I just divide by 100, 0.98930. That percent abundance gets multiplied by the isotopic mass for this isotope carbon 12, which is exactly 12, and I gave you 4 zeros past the decimal point. Atomic mass units. Add to this a term for carbon 13. The percent abundance we figured out is 1.070%. Converted to decimal form, again, that's 0.0107 multiplied by the mass of that isotope carbon 13, 13.00335 AMU. Again, note that this first term corresponds to all the information we have for carbon 12, the second term to all the information we have for carbon 13, and if we had more isotopes of carbon to deal with, we simply would have tacked on extra terms to account for those extra isotopes. We're not going to divide anything through. All of that weighting is factored into consideration in these percentages that we've converted to decimals out in front of each leading term. Now, all we have to do is some math. We multiply this first term out and the second term out. When we multiply this first term, we get a calculator answer of 11.8716, but note that we need to keep just 5 significant digits. 1, 2, 3, 4, 5 sig figs here, an unlimited number of sig figs in this quantity since it's an exact number, but significantly more than 5, as obvious from this quantity. So our calculator result gives us 11.8716, of which only the first 5 digits are significant. Figuring out the computation for the second term proceeds similarly, except we're only going to need 4 significant digits here. Our calculator result gives us approximately 0.139135, and so on. Again, only the first 4 of these digits are significant. When we add these two terms together to get our final result, we end up with 12.011. We have 3 significant digits past the decimal point in this first term. We have 4 significant digits past the decimal point in the second term, and the rule for adding with sig figs is to keep the fewest digits past the decimal point as any term has. So we keep 3 significant digits past the decimal point when we add. This is our reported average for carbon's isotopes. If you have a periodic table handy nearby, you can check to confirm that this is similar to what's reported on the periodic table. 12.011 to 3 digits past the decimal point matches the periodic table's average mass. And so this is where those numbers come from for those average masses seen on the periodic table.